What if two objects could whisper secrets to each other instantly, no matter how far apart they were in the universe? Imagine throwing a pair of magical dice, one here on Earth, the other on a distant planet light years away. And no matter how many times you rolled them, they'd always land on matching numbers, as if controlled by some unseen force. This isn't science fiction, it's real, and it's called quantum entanglement. Einstein himself called it spooky action at a distance because it defies every rule of physics as we know it. Think of it like cosmic twins, particles born together, forever linked in a way that's so bizarre, even the brightest minds struggle to explain it. When one changes its state, the other instantly mirrors it, faster than the speed of light, as if space and time don't apply to them. Now here's the wild part. This isn't just some abstract idea tucked away in a lab. Quantum entanglement could rewrite the future of technology, from unhackable communication networks to computers so powerful, they'd solve problems in seconds that would take today's supercomputers centuries. But how does it work? How can particles separated by galaxies somehow stay in perfect sync? The answer lies in the heart of quantum mechanics, a realm where reality behaves in ways that feel almost dreamlike. Imagine tossing a coin and seeing it land as both heads and tails at the same time until you look, and then it chooses one. That's the quantum world for you, unpredictable, mysterious, and utterly fascinating. This video is your ticket to unraveling one of the universe's greatest mysteries. We'll break down the science without the jargon, explore mind-blowing experiments that prove entanglement is real, and show you how this spooky phenomenon might soon revolutionize everything from medicine to space travel. By the end, you'll see the universe and the tiny particles dancing within it in a whole new light. So if you're ready to have your mind stretched, buckle up. We're diving into the quantum realm, where the rules you know don't apply and the possibilities are infinite. Einstein may have famously dismissed quantum entanglement as spooky action at a distance, but the story begins with a fiery debate among some of the greatest minds in physics. In 1935, Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a groundbreaking paper known as the EPR paradox. Their goal: to expose what they saw as a glaring flaw in quantum theory. The problem was that entangled particles, once linked, seemed to influence each other instantaneously, even if separated by vast cosmic distances. This, Einstein argued, violated the sacred speed limit of the universe, the speed of light, a cornerstone of his own theory of relativity. How could information travel faster than light? To him, it simply couldn't. There had to be hidden variables, unknown properties guiding the particle's behavior, making the whole thing less mysterious and more classical. But the quantum world had other ideas. Niels Bohr, Einstein's intellectual rival, fired back with a radical counterargument. Reality at the smallest scales doesn't play by the rules we're used to. In the quantum realm, particles don't have definite states until they're measured. It's as if the universe itself is holding its breath, waiting for observation to collapse all possibilities into a single outcome. The EPR paper wasn't just a critique, it was a gauntlet thrown down, sparking decades of experiments to settle the score. Early researchers like John Bell later devised ingenious tests to see who was right. And what they found would shake the foundations of physics. Picture this: a lab in the mid-20th century, chalkboards covered in equations, scientists hunched over detectors, racing to catch a glimpse of these ghostly connections between particles. The results: entanglement wasn't just real, it was stranger than even Einstein had feared. Particles really were communicating faster than light, not by sending signals, but through a deeper, weirder link that bypassed space and time entirely. This wasn't magic, it was the universe revealing its hidden wiring, proving that at its core, reality is far more interconnected than we ever imagined. And here's the twist: Einstein's skepticism, his very resistance to the idea, ended up pushing quantum mechanics further than anyone expected. His spooky label stuck, but the phenomenon he doubted became one of the most rigorously tested and validated concepts in modern science. From those early debates to today's quantum labs, the EPR paradox didn't break physics. It exposed a truth far more extraordinary than anyone had dreamed. While Einstein and Bohr clashed over the paradox, another giant of physics stepped into the ring: Erwin Schrödinger, the man who gave quantum mechanics its most iconic equation and its strangest metaphor. It was Schrödinger who first labeled this bizarre connection between particles: entanglement, a word that perfectly captured how deeply intertwined their fates became. But his real masterstroke came when he took the math out of the lab and into our imaginations with a thought experiment so vivid, it's haunted pop culture ever since: Schrödinger's cat. Picture a sealed box with a feline inside, a vial of poison, and a tiny quantum trigger, say a single radioactive atom. If the atom decays, the vial breaks. If it doesn't, the cat lives. But here's the kicker: according to quantum rules, until someone opens the box, that atom exists in a superposition. It's both decayed and not decayed at the same time. And so, grotesquely, the cat is both alive and dead, a blur of possibilities until observation forces reality to pick a side. Schrödinger wasn't just being macabre. He was spotlighting how absurd quantum weirdness feels when scaled up to our everyday world. The cat's fate mirrors entangled particles. Their states aren't just unknown, they're undefined until measured, with each particle's choice instantly determining its partners, no matter the distance. It's as if the universe refuses to settle on a concrete reality until forced to. But here's where it gets trippier. Schrödinger realized entanglement wasn't rare, it was inevitable. Anytime particles interact, they can become entangled, weaving an invisible web of connections across the cosmos. His work showed that superposition and entanglement weren't glitches, they were fundamental features of nature hiding in plain sight. While Einstein wrestled with the spookiness, Schrödinger framed it as the universe's ultimate magic trick. Reality itself is a cosmic game of peekaboo, only revealing its cards when we look. And that's the genius of the cat. It takes quantum mechanics, a theory drowning in abstract math, and makes it visceral. You don't need equations to feel the unease of a cat neither alive nor dead, just as you don't need a lab to grasp two dice always rolling matching numbers across galaxies. Schrödinger's playful nightmare did more than shock. It gave us a language to talk about the impossible. Because sometimes, to understand the universe, you need a metaphor that's half genius, half madness, and completely unforgettable. The debate between Einstein and Bohr might have seemed like a philosophical stalemate until a quiet Irish physicist named John Stuart Bell stepped in with a mathematical sledgehammer. In 1964, Bell published a paper so revolutionary, it cut through decades of argument like a laser through fog. His theorem didn't just challenge Einstein's hidden variables, it gave scientists a way to test once and for all who was right. At its core, Bell's theorem was a set of inequalities, mathematical rules that any classical system, including Einstein's hidden variables, would have to obey. But quantum mechanics, it shattered those rules. Imagine two detectives interrogating suspects in separate rooms. If the suspects' answers matched perfectly every time, even though they couldn't communicate, you'd assume they'd prearranged their stories. That's Einstein's hidden variables at work. But Bell showed that entangled particles behave like suspects whose answers match too well, beyond what any prearranged script could explain, the only way to account for their perfect coordination. A connection that bypasses space and time entirely. The real brilliance of Bell's work was turning philosophy into experiment. His inequalities gave researchers a recipe: measure entangled particles in different directions and compare their states. If the results violated Bell's inequalities, which quantum mechanics predicted they would, then hidden variables couldn't be the answer. And when physicists like Elaine Aspect ran these tests in the 1980s, the results were unequivocal. Entangled particles did violate Bell's limits, behaving in ways that no classical theory could explain. Think of it like a cosmic magic trick where the magician's deck of cards changes color based on how you choose to look at it. Bell's theorem revealed that the universe isn't just weird, it's fundamentally weird. There's no hidden script, no secret handshake between particles. Instead, their connection is instantaneous, a ghostly synchronization that makes a mockery of distance. This wasn't just a win for Bauer's interpretation, it was a wake-up call. Reality at its deepest level doesn't play by the rules of locality or causality we're used to. Bell's theorem didn't just settle a debate, it redefined what we thought was possible, proving that entanglement isn't a bug in the universe's code. It's a feature written into the fabric of existence itself, and that realization didn't just change physics. It opened the door to technologies we're only beginning to dream of. Elaine Aspect didn't just test Bell's theorem, he turned quantum weirdness into undeniable fact. In the early 1980s, his team at the Institut d'Optique in France designed an experiment so precise it left no room for doubt. They started with a simple but brilliant setup, a source that spat out pairs of entangled photons, particles of light linked in perfect harmony. These photons were then sent racing in opposite directions toward detectors set at different angles. The key, measuring their polarization, the direction they wiggle as they travel at the exact same moment. Here's where it gets wild. If Einstein's hidden variables were real, the photon's behavior would have followed strict, predictable rules. But Aspect's results were anything but predictable. No matter how far apart the photons were or how quickly the detector's angles were changed, their polarizations matched in ways that defied classical physics. It was as if each photon knew what its partner was doing instantaneously, even though no signal could have traveled between them fast enough to coordinate. The universe, it seemed, had no speed limit for entanglement. To grasp just how groundbreaking this was, picture two dancers spinning in pitch darkness, miles apart, yet somehow mirroring each other's every move flawlessly, without any cue or communication. Aspect's experiment proved that entangled particles don't just appear connected, they are connected, bound by a thread that ignores space and time. His work didn't just confirm Bell's predictions, it shattered the very notion of locality, the idea that objects are only influenced by their immediate surroundings. The implication sent shockwaves through physics. Suddenly, the spookiness Einstein dismissed wasn't just theoretical, it was measurable, repeatable, real. Aspect's meticulous setup ruled out every possible loophole, leaving skeptics with no escape. Even today, his experiments stand as a cornerstone of quantum mechanics, proving that reality at its smallest scales operates on rules far stranger than fiction. And the most thrilling part, this wasn't the end, it was the beginning. Because once we accepted entanglement as fact, the door swung open to technologies that could reshape our world. Quantum entanglement is the universe's ultimate game of cosmic telephone, except there's no delay, no static, and no distance limit. At its core, it's a phenomenon where two or more particles become so deeply linked that the state of one instantly influences the state of the other, no matter how far apart they are. Picture a pair of dice rolled simultaneously on opposite ends of the galaxy. In our everyday world, they'd land randomly, maybe a 3 here, a 5 there. But in tangled dice, they'd always show the same number, as if controlled by an invisible thread stretching across the cosmos. Now, let's break down the jargon. A quantum state is simply the condition of a particle, like whether it's spinning up or down, or polarized horizontally or vertically. Think of it as the particle's secret identity, hidden until you measure it. Correlation is what makes entanglement so mind-bending. Normally, if you flip two coins, their outcomes are independent heads or tails with no connection. But entangled particles are like coin flips that always match, even if you change how you flip them mid-air. It's not just coincidence, it's as if the coins share a single fate decided the moment you look at one. Here's another way to visualize it. Imagine you have a pair of magical gloves. You toss one glove into a spaceship headed for Mars, keeping the other in your pocket. The moment you open your hand and see you're holding the left-handed glove, you instantly know the one on Mars is the right-handed one, no signal needed. That's entanglement in action. The gloves didn't communicate, their states were always tied together, a single system split across space. But here's where it gets even stranger. Unlike those gloves, entangled particles don't have defined states until you measure them. It's as if each particle exists in a haze of all possible states at once, and the act of observing one forces its twin to snap into the corresponding state, like a mirror suddenly reflecting your expression. This isn't just theoretical, it's been proven in labs time and again, with particles separated by hundreds of miles still behaving as one. So why does this matter? Because entanglement isn't just a quirk of tiny particles. It's a glimpse into the universe's hidden wiring, revealing a reality far more interconnected than we ever imagined. And as we'll see next, this spooky connection isn't just a curiosity, it's the foundation for technologies that could redefine the future. Let's zoom in on one of the most mind-bending examples of quantum entanglement, the spin of particles. Picture an electron, that tiny, buzzing cornerstone of atoms, spinning like a top. But here's the catch. In the quantum world, spin isn't about physical rotation. It's more like an intrinsic property, a built-in compass needle pointing either up or down. Now, imagine two electrons born from the same quantum event, their spins entangled. They're like a pair of cosmic dancers with a secret pact. If one spins up, the other must spin down, no matter where they are in the universe. This isn't just a neat trick, it's a fundamental rule. When these entangled electrons are separated, even by thousands of miles, measuring one spin instantly locks its partner into the opposite state. It's as if the universe has an invisible ledger, keeping track of their connection faster than light could ever travel. Scientists call this spin correlation, and it's the backbone of countless quantum experiments. To visualize this, think of a pair of magic coins. You flip one and it lands heads immediately. Its entangled twin flips to tails, no matter if it's in your hand or on the other side of the galaxy. There's no signal passing between them, no hidden wire. The connection is instantaneous, defying every classical notion of cause and effect. But how do we know this isn't just a prearranged agreement? That's where the elegance of spin entanglement shines. Unlike gloves or coins, quantum particles don't have a definite spin until measured. They exist in a fuzzy superposition of both states, like a coin mid-toss, neither heads nor tails. The act of measuring one particle doesn't just reveal its spin, it creates it while simultaneously forcing its entangled partner into the opposite state. It's as if the universe refuses to let these particles have independent identities, binding them together in a relationship so tight, not even space can pry them apart. This phenomenon isn't just theoretical. Labs around the world have tested spin entanglement with electrons, photons, and even entire atoms, consistently finding the same eerie synchronization. It's a reminder that at the quantum level, the universe operates on rules that feel less like physics and more like poetry, where particles whisper to each other across the void, and the very act of looking changes what's there. And this isn't just a curiosity. Spin entanglement is the engine powering breakthroughs like quantum computing and ultra-secure communication, proving that the universe's weirdest features might just hold the keys to our future. Inside a dimly lit lab, a laser beam slices through the darkness, striking a special crystal with atomic precision. In that instant, like magic, the crystal spits out pairs of photons, particles of light born entangled. These photon twins share an unbreakable bond, their fates intertwined no matter how far they're pulled apart. Scientists capture this quantum ballet using tools so precise they'd make a Swiss watch look crude. At the heart of the setup sits a beam splitter, a device so simple yet so powerful it's like a cosmic traffic cop for light. When an entangled photon hits this splitter, it faces a choice: go left or right. But here's the twist: its entangled partner, even if it's miles away, will always make the opposite choice at the exact same moment. No signal passes between them. No hidden wires, just pure, instantaneous correlation, as if the universe itself flipped a coin and declared both outcomes at once. Detectors flanking the splitter act as the jury in this quantum courtroom. They record each photon's path with nanosecond timing, hunting for mismatches. Classical physics predicts some randomness, like two friends occasionally picking different pizza toppings. But entangled photons, they're in lockstep, their choices synced with near-perfect harmony, defying the odds. Modern experiments stretch this eerie connection across entire cities. In one groundbreaking test, researchers in China beamed entangled photons from a satellite to ground stations over 700 miles apart. The result: the particles stayed perfectly in sync, as if distance meant nothing. The real genius lies in how scientists use these setups to pry open quantum mechanics' deepest secrets. By tweaking the angles of polarizers' filters that force photons to pick a direction, they've proven that entanglement isn't just strong, it's unbreakable by classical rules. Imagine two pianists playing a duet on opposite sides of the planet, never missing a note, never needing sheet music. That's the level of coordination we're talking about. Every experiment chips away at the idea that particles are independent actors, revealing instead a universe stitched together by threads we're only beginning to trace. And the implications, they're staggering. Labs now use these photon pairs to test quantum encryption, build unhackable networks, and even probe the nature of spacetime itself. What started as a laser hitting a crystal has become a window into reality's most profound mysteries, one photon at a time. Einstein's theory of relativity has one ironclad rule: nothing can outtrace light. It's the universe's ultimate speed limit, a cosmic traffic law woven into the fabric of spacetime itself. But quantum entanglement gleefully tosses that rule out the window. When two entangled particles sync their states instantaneously across galaxies, they're not just bending relativity, they're shattering it. Or are they? Here's the brilliant loophole that keeps physicists from tearing up their textbooks. Entanglement doesn't actually send information. Think of it like this: you and a friend each hold one end of a jump rope standing miles apart. If you flick your wrist, the ripple takes time to travel down the rope. That's relativity in action, but entanglement, it's as if the rope doesn't exist. Your friend's end moves simultaneously with yours, defying the delay. The catch: you can't use this link to send a message. The movement is random, unpredictable. Without knowing how you flicked your wrist first, your friend just sees noise. That's the heart of the loophole. While entangled particles dance in perfect sync, their coordination is useless for communication. There's no way to encode a signal, no method to force one particle into a specific state that the other would reliably mirror on demand. This subtle distinction saves relativity from collapse. Einstein's speed limit still holds because usable information, the kind that could transmit "meet me at Mars by Tuesday," can't be beamed faster than light. The universe's rulebook remains intact, even as entanglement reveals a layer of reality where spacetime feels optional. But don't mistake this loophole for a trivial detail. It's what makes entanglement both maddening and miraculous. The particles aren't whispering secrets, they're holding up mirrors to a deeper truth. The universe is fundamentally interconnected in ways that transcend distance, even if we can't hijack that connection to build a hyper-speed phone. It's like discovering a hidden subway beneath your city, one that shuttles passengers at infinite speed, but only if they're wearing blindfolds and don't care where they're going. You can't use it to commute, but its existence rewrites how you understand the streets above. This dance between quantum weirdness and cosmic rules isn't a flaw, it's a feature. Entanglement doesn't break the universe, it reveals that the universe has more layers than we imagined. And that revelation is what fuels the next frontier of physics, where the answers might not just defy Einstein's expectations, they could redefine reality itself. The idea of teleportation usually conjures images of sci-fi beams whisking people between stars, but quantum teleportation is something far stranger and more exciting. Forget moving matter, this is about teleporting information, the very essence of a particle's quantum state across space in the blink of an eye, thanks to entanglement. The first real-world proof came in 1997 when a team of scientists pulled off what seemed like magic. They teleported the polarization state of a photon from one corner of their lab to another without it ever physically crossing the distance. Here's how it worked. The researchers started with 3 photons. Let's call them photon A, the sender, photon B, the receiver, and photon C, the message. Photons B and C were entangled, sharing that eerie, instantaneous bond we've been exploring. Now, here's the clever part. The team made photon A, the one carrying the quantum state to be teleported, interact with photon B. This interaction created a ripple in the quantum connection between B and its entangled partner, photon C. Like a game of subatomic telephone, the moment photon A's state was measured, its information vanished from its original location and reappeared in photon C, as if by sleight of hand. But wait, there's a catch. This isn't a Star Trek replicator. The original photon wasn't moved. Its quantum state was destroyed in the process, adhering to the no-cloning theorem, which forbids copying quantum information. Instead, its essence was reconstructed in photon C, thanks to the entanglement bridge. It's like burning a handwritten letter and magically having its words reappear on a blank page miles away. Only the ink is quantum properties and the fire is a beam splitter in a lab. The experiment's brilliance lay in its use of what's called a Bell state measurement. By comparing photons A and B, the team extracted just enough information to program photon C into mirroring photon A's original state, all while preserving the secrecy of the quantum data. No peeking, no cheating, just pure quantum weirdness at work. And the kicker, this teleportation isn't limited by distance. Later experiments stretched the gap from meters to kilometers, even across continents, using satellites to beam entangled photons between ground stations. What makes this more than a parlor trick is the sheer defiance of classical logic. Teleporting a quantum state doesn't rely on speed or physical travel. It exploits the universe's hidden wiring, where entangled particles are 2 sides of the same coin, no matter how far apart. This isn't just about photons in a lab. It's a blueprint for a future where unhackable quantum networks could shuttle sensitive data across the globe, where quantum computers might one day teleport calculations between nodes faster than light could ever hope to travel. The 90s experiment was just the first step into a world where information doesn't move through space, it simply appears, as if the universe itself hit copy-paste. Imagine sending a pair of entangled photons on a journey through the void of space, their fragile quantum link stretching farther than ever before across continents, across mountain ranges, even across the curvature of the Earth itself. That's exactly what China's MICIUS satellite achieved in 2016, shattering records by beaming entangled particles over 1,200 kilometers apart. This wasn't just a lab experiment scaled up, it was a quantum leap toward a future where the entire planet could be woven together by an invisible web of entanglement. Why space? Because Earth's atmosphere is the enemy of delicate quantum states. Photons traveling through air collide with molecules, scattering like ripples in a stormy pond. Over long distances, this interference can destroy entanglement, snapping the fragile thread between particles. But in the vacuum of space, there's nothing to disrupt their connection. MICIUS, named after the ancient Chinese philosopher Mozi, who pioneered optics, acted as a cosmic middleman, generating pairs of entangled photons aboard the satellite and firing them toward 2 ground stations in China. The distance between those stations, roughly the width of France, and yet, despite hurtling through the freezing darkness of orbit, the photons arrived perfectly synced, their quantum bond intact. The technical hurdles were staggering. Aligning the satellite's photon beam with ground-based receivers required precision akin to threading a needle from the edge of the stratosphere. Even the slightest vibration or thermal drift could send the photons veering off course. To pull it off, engineers developed ultra-sensitive tracking systems that adjusted the beam's aim in real time, compensating for the satellite's blistering orbital speed, nearly 28,000 kilometers per hour. The result, a signal so stable, it proved entanglement could survive journeys longer than ever imagined. But MICIUS wasn't just breaking records, it was laying groundwork for a revolution. Picture a globe-spanning quantum internet, where satellites relay unhackable encryption keys between cities, or where quantum computers in Tokyo and New York collaborate as if they were side by side. Traditional fiber optic cables lose quantum signals after a few hundred kilometers, but space-based entanglement could bridge oceans. China's experiment showed it's possible, and since then, other nations have raced to launch their own quantum satellites, turning the sky into a testing ground for the next communications paradigm. The real magic lies in what this means for security. Quantum networks built on entanglement don't just encrypt data, they make eavesdropping physically impossible. Any attempt to intercept the photons would sever their quantum link, alerting users instantly. It's like sealing a letter with wax that melts if touched, except the wax is woven into the fabric of reality itself. MICIUS proved that such a system isn't science fiction, it's engineering happening right now with satellites as the linchpin, and this is just the beginning. Future missions could deploy constellations of quantum satellites, creating a mesh of entanglement encircling the planet. Imagine a world where bank transfers, medical records, even voting systems are secured by the unbreakable laws of quantum physics. MICIUS didn't just send photons spinning through space, it launched humanity into a new era of connectivity, one where the universe's spookiest phenomenon becomes the backbone of our digital future. The stars, it turns out, might hold the keys to our most pressing earthly challenges. The race to build the quantum internet isn't just a scientific endeavor, it's a geopolitical sprint with nations pouring billions into entanglement-based networks that could redefine global power dynamics. Europe's Quantum Internet Alliance is stitching together a continent-spanning web, where labs from Delft to Vienna share quantum-secured data through fiber optic threads laced with entangled photons. Their secret weapon, quantum repeaters, devices that act like signal boosters for fragile quantum states, stretching entanglement across hundreds of kilometers without breaking the link. Picture a relay race where the baton isn't passed but teleported between runners, each handoff perfectly synchronized by the laws of quantum physics. Across the Atlantic, the U.S. is taking a different tack. Instead of betting solely on fiber, American researchers are hybridizing quantum and classical systems, using quantum repeaters that can plug into existing internet infrastructure. Projects like the Department of Energy's Chicago Quantum Exchange are turning the Windy City into a testbed, with entangled photons zipping between Argonne National Laboratory and Fermi Lab like digital carrier pigeons. The goal, a network where quantum encryption protects everything from power grids to stock trades, all while leveraging the backbone of today's web. But the most audacious player might be China, fresh off their MICIUS satellite triumph. Their next move, a hybrid space and ground quantum network, with satellites knitting together ground stations from Beijing to Shanghai. It's like building a celestial switchboard where beams of entangled light crisscross the atmosphere, immune to the signal decay that plagues terrestrial fiber. Meanwhile, Japan's Quantum ICT Lab is pioneering quantum memory, nodes devices that store entangled states like batteries hoarding energy, ready to release perfect synchronization on demand. The stakes more than just bragging rights. Whoever cracks the quantum internet first could set the standards for a new era of unhackable communication, dominating finance, defense, and data sovereignty. Imagine a world where sensitive diplomatic cables or billion-dollar transactions flow through channels so secure, eavesdropping becomes a physical impossibility. The irony, this cutthroat race hinges on the very phenomenon Einstein called spooky, a ghostly connection that now might just bind the future of nations. Yet for all the competition, there's a quiet collaboration humming beneath the surface. Scientists from rival nations still share findings at conferences because quantum mechanics doesn't respect borders. The same entanglement that could someday shield state secrets is, for now, reminding us that discovery thrives when minds intertwine no matter how far apart they seem. Entanglement isn't just a curiosity, it's the rocket fuel powering the quantum computing revolution. At the heart of this revolution lies the qubit, quantum computing's answer to the classical bit. But unlike ordinary bits that toggle between 0 and 1, qubits exploit entanglement to exist in a superposition of both states simultaneously. Picture a coin spinning in midair, not heads or tails, but both at once until it lands. Now imagine a million such coins, all flipping in perfect sync, their outcomes intertwined. That's the raw computational muscle entanglement unleashes. Here's how it transforms processing power. Classical computers solve problems step by step, like climbing a ladder one rung at a time. Quantum computers, they take every possible path at once. When qubits become entangled, their superpositions link together, creating a vast web of parallel computations. Think of it like navigating a maze. A classical computer must try each corridor sequentially, while a quantum machine explores all routes simultaneously, instantly finding the exit. This isn't just speed, it's a fundamentally different way of processing information. Take factoring large numbers, the mathematical backbone of modern encryption. A supercomputer might take millennia to crack a 2048-bit code, but a quantum computer with entangled qubits could, in theory, solve it in hours. How? By testing every possible factor in parallel, as if an army of mathematicians worked in perfect unison. This brute force parallelism is why entanglement isn't just useful, it's revolutionary. Yet entanglement's power comes with quirks. Qubits are notoriously delicate, their quantum states collapsing at the slightest disturbance, a phenomenon called decoherence. It's like trying to keep those spinning coins balanced midair while a storm rages around them. That's why quantum computers operate in near absolute zero temperatures, shielded from magnetic fields and even stray photons. The challenge, scaling this fragility into practical machines. The payoff, though, could redefine entire industries. Drug discovery, for instance, relies on simulating molecular interactions, a task so complex classical computers often approximate. Quantum computers could model every atom in a protein simultaneously, accelerating cures for diseases. Financial markets could optimize global portfolios in real time, and AI might uncover patterns buried in petabytes of data. All because entangled qubits don't just compute, they dance across infinite possibilities at once. This isn't futuristic speculation. Companies like IBM and Google already run cloud-accessible quantum processors, while startups race to build error-corrected qubits. The machines are still in their infancy, prone to mistakes and limited in scope, but the trajectory is clear. Entanglement isn't just rewriting physics, it's scripting the next chapter of human innovation. And the most exciting part, we're only flipping the first few coins in what could become an unimaginable computational avalanche. Quantum cryptography doesn't just lock data behind complex algorithms, it weaponizes the weirdness of entanglement to create codes that physically can't be cracked. Here's how it works. Imagine two people, Alice and Bob, want to share a secret message. Instead of relying on math problems that supercomputers might eventually solve, they use a pair of entangled photons. Each photon's polarization, whether it wiggles horizontally or vertically, becomes a piece of their encryption key, generated randomly by the quantum connection between them. The magic lies in what happens if an eavesdropper, say Eve, tries to intercept these photons. The moment Eve attempts to measure a photon's polarization to steal the key, she collapses its quantum state. It's like trying to read a letter written in invisible ink that burns up the second you shine light on it. Her interference severs the entanglement, introducing errors Alice and Bob can detect by comparing a small sample of their keys. If the error rate spikes, they know someone's listening, not because of clever coding, but because the laws of physics won't allow secrecy to be violated without leaving traces. This isn't just encryption, it's a built-in alarm system woven into reality itself. The most striking example of this is quantum key distribution, or QKD, a protocol first proposed in the 1980s. In practice, it looks like this. Alice sends Bob a stream of entangled photons, each one encoding a bit of their shared key, 0 or 1, based on its polarization. But here's the catch. Eve can't copy the photons thanks to the no-cloning theorem, which forbids duplicating quantum states. Even if she captures one, she can't resend it without altering its state, tipping off Alice and Bob. It's the ultimate security feature, tamper-proof by design, not just by difficulty. Real-world applications are already live. Banks in Switzerland and government agencies in China use quantum-secured fiber networks to transmit sensitive data. In Vienna, researchers demonstrated a quantum-secured video call between two city halls, with encryption keys generated by entangled photons traveling through underground cables. The system didn't just block hackers, it made hacking attempts visible, like a burglar triggering laser tripwires in a vault. But the true power of quantum cryptography lies in its future potential. Picture a world where power grids, elections, and medical records are shielded by networks that don't just resist breaches but expose them the instant they occur. Unlike classical encryption, which erodes as computers grow faster, quantum security is timeless, rooted in the unbreakable laws of physics. It's not a stronger lock. It's a lock that shatters the moment someone touches it, leaving no doubt they were there, and that changes everything. Time crystals sound like something ripped from a sci-fi novel, structures that pulse rhythmically, not in space but in time, defying our most basic laws of physics. And yet, in 2016, researchers did the unthinkable. They created these bizarre objects in the lab, stitching together entangled particles that dance to a never-ending beat without any energy input. Picture a clock that ticks forever without winding, or a pendulum that swings perpetually without gravity. That's the eerie beauty of time crystals. Their motion isn't powered by external forces but locked into the universe's own quantum rhythm. At the heart of this phenomenon is entanglement's latest magic trick. Normally, perpetual motion is impossible because of entropy, the universe's relentless push toward disorder. But time crystals sidestep this rule by existing in a peculiar quantum dance where particles remain entangled across time, not just space. Imagine a row of dominoes that don't just fall in sequence but also reset themselves the moment they topple, looping endlessly without friction or decay. That's the essence of a time crystal, a system that doesn't settle into equilibrium but oscillates between states indefinitely, its structure echoing across time like a ripple frozen in a pond. A breakthrough came when scientists like Nobel laureate Frank Wilczek theorized that certain quantum systems could break time translation symmetry, a fancy way of saying they don't play by the usual rules where time flows uniformly. Instead, these systems tick at regular intervals like a metronome built into the fabric of reality. To build one, teams at Harvard and the University of Maryland used chains of ytterbium ions entangled and nudged with precise laser pulses. The result, a lattice of particles that flipped back and forth between two configurations, not because of energy added, but because entanglement forced them to keep time. Here's where it gets even wilder. Time crystals aren't just curiosities, they're a new phase of matter, as distinct from solids or liquids as ice is from steam. They hint at a world where entanglement doesn't just link particles across distance, but stitches together moments in time, creating structures that exist in a looping, persistent now. And the implications: they could revolutionize everything from quantum memory storing data in indestructible time loops, to ultra-precise sensors that never drift out of sync. But perhaps the most mind-bending thought is this: time crystals might be proof that the universe has hidden gears ticking beneath the surface of reality. They're not powered by energy, they're sculpted by entanglement's invisible hand, a reminder that the quantum world doesn't just defy our expectations, it rewrites them entirely. And if we can harness their rhythm, we might finally unlock technologies that operate outside time's relentless march, dancing to a beat only quantum physics can hear. Plants might seem like the last place to hunt for quantum weirdness until you peek inside their leaves. Hidden beneath the calm green surface, photosynthesis plays out like a molecular ballet where sunlight spins into sugar, and entanglement might just be the choreographer. In 2007, a team of scientists studying green sulfur bacteria algae that thrive in the dimmest ocean depths stumbled onto something extraordinary. These organisms achieved near-perfect energy efficiency, converting 95% of absorbed sunlight into usable power. For comparison, the best solar panels today barely crack 20%. The secret: a quantum trick called coherence, where light-harvesting molecules act like entangled antennas, tuned to harvest every photon in perfect unison. Picture a vast solar farm with millions of panels. Normally, energy bounces randomly between them with losses at every step, but in these algae, the system works more like a frictionless highway. When a photon strikes one of the leaf's light-capturing pigments, the energy doesn't hop haphazardly toward the reaction center where photosynthesis happens. Instead, it explores all possible paths at once, guided by quantum coherence. It's as if the algae hold a map of every route in advance, choosing the most efficient one in real time. The energy moves like a wave, not a particle, avoiding dead ends and maximizing speed, and the glue holding this quantum search together: entanglement. The evidence came from ultra-fast laser experiments that tracked energy transfer in femtosecond's millionths of a billionth of a second. Researchers saw energy signatures that could only exist if the algae's pigments were entangled, their states linked in a way that let them test multiple pathways simultaneously. Think of it like a maze runner who doesn't just turn left or right but splits into copies, scouting every corridor at once, then collapses into the single version that found the exit. This isn't just efficient, it's a survival hack forged by evolution. In the deep sea, where sunlight is scarce, missing even one photon could mean death. Quantum coherence turns scarcity into abundance. What's jaw-dropping is how robust this process is. In the lab, quantum states usually crumble at the slightest jostle from heat or vibration. But inside a living cell, a warm, wet, chaotic environment, these algae maintain coherence far longer than anything engineers can replicate. It's like discovering a symphony orchestra playing flawlessly in the middle of a hurricane. Scientists suspect proteins surrounding the pigments act as quantum chaperones, shielding the delicate entangled states just long enough to work their magic. This discovery rewrites the boundaries between biology and quantum physics. Plants and algae may have been leveraging entanglement for billions of years, long before humans labeled it spooky. And the implications stretch beyond leaves. If nature cracked quantum-enhanced energy harvesting, could we? Labs are already racing to mimic these systems, designing bio-inspired solar cells that borrow coherence to boost efficiency. Imagine coatings for buildings that photosynthesize like algae, or crops engineered to thrive in shade by squeezing every drop of light. The quantum revolution isn't just happening in supercooled labs. It's been humming quietly in every garden, forest, and ocean, waiting for us to notice. And the lesson is clear: sometimes the most advanced technology isn't human-made. It's photosynthesis perfected by evolution, with entanglement as its silent partner. Black holes, those cosmic vacuum cleaners where even light can't escape, might be hiding the universe's most unexpected secret wormholes threaded by entanglement. In 2013, physicists Juan Maldacena and Leonard Susskind dropped a bombshell theory. What if Einstein's so-called spooky action at a distance wasn't just a quantum fluke, but a literal shortcut through spacetime? They called it ER equals EPR, a daring equation that stitches together two of Einstein's ideas: entanglement from the EPR paradox and wormholes Einstein-Rosen bridges. The claim: every pair of entangled particles might be joined by a microscopic tunnel through the fabric of reality, a wormhole so tiny it makes a human hair look planetary. Think of it like this: you're on opposite sides of a mountain, and your friend holds one end of a rope while you grip the other. Normally, tossing a message across would take hours. But if the rope secretly tunnels through the mountain, you could tug it instantly, no signal delay, just a hidden connection. That's the ER equals EPR proposal. Entanglement isn't magic, it's geometry. The math suggests that when particles become entangled, space-time itself warps to form a bridge between them, shorter than the space separating them. It's as if the universe, faced with the problem of keeping these particles in sync, simply cheated by bending the rules of distance. But how could a wormhole, a staple of sci-fi warp drives, lurk inside something as mundane as two photons? The answer lies in holography, a wild concept where our three-dimensional universe might be a projection of information stored on a two-dimensional surface, like a cosmic DVD. In this view, entanglement doesn't just link particles, it creates space-time. Picture a spiderweb where each silk strand represents an entangled pair. The more strands, the more complex the web, and the more structured the space between them becomes. Wormholes, then, are the threads weaving reality together. Here's where it bends the mind further. Normally, wormholes are unstable, snapping shut faster than you can say, interstellar road trip. But entanglement might be the glue holding them open. The same quantum connection that syncs particle states could prevent these spacetime tunnels from collapsing, acting like cosmic scaffolding. It's a twist even Einstein didn't see coming. The phenomenon he dismissed might be the very thing enabling his own hypothetical bridges. The implications are staggering. If ER equals EPR holds, the quantum realm and gravity aren't separate puzzles, they're two sides of the same coin. Black holes, those gravity monsters, might be entangled with distant partners through wormholes, their interiors secretly linked. This could solve mysteries like how information escapes a black hole instead of vanishing forever. Maybe it doesn't. Maybe it just takes a shortcut, of course. This is still theoretical. No one spotted a wormhole in a lab yet. But experiments with quantum computers are testing the idea by simulating spacetime geometries. The results so far: entangled qubits behave as if they're connected by wormholes, with their correlations matching the math. It's early days, but the thread between entanglement and spacetime is getting harder to ignore. So next time you hear about spooky action, remember, the spookiness might not be in the particles, but in the fabric beneath them. The universe isn't just stranger than we imagined. It might be literally woven together by invisible tunnels, stitching reality into a seamless whole. And if we ever learn to tug those threads, the future of physics, and maybe even travel, could look very different indeed. If the universe has a secret hiding in plain sight, it might be this. Everything we see, stars, planets, even your morning coffee, could be nothing more than a dazzling illusion, a hologram projected from information stored on a two-dimensional surface at the edge of space. This isn't science fiction. It's the holographic principle, a radical idea born from the fiery intersection of black hole physics, string theory, and the mind-bending behavior of entanglement. The trail of clues starts with black holes, those cosmic shredders where gravity is so strong, not even light escapes. But here's the puzzle. When matter falls into a black hole, what happens to the information it carried? According to quantum mechanics, information can't be destroyed. It's a sacred rule. Yet black holes seem to vaporize it into oblivion. Enter entanglement entropy, a concept that ties this paradox to the holographic principle. When particles near a black hole's event horizon become entangled, their quantum states create a kind of information footprint on the surface of the horizon itself. It's as if the black hole's 3D interior is projecting its data onto a 2D screen, like a movie being encoded onto a DVD. String theorists took this further, suggesting that our entire universe might work the same way. Imagine the cosmos as a vast, swirling hologram where every galaxy, every atom, is just a projection of underlying data written on a distant, flat boundary. The math reveals something staggering. The maximum amount of information you can pack into any volume of space isn't determined by its 3D size. It's limited by the area of its 2D surface. That's like saying the content of your hard drive isn't stored inside it but on its outer shell. Here's where entanglement becomes the star of the show. The fabric of spacetime itself might be woven from quantum connections, with entangled particles acting like microscopic needles stitching together the holographic illusion. Think of it as cosmic pixelation. The tighter the entanglement, the sharper the projected reality. This could explain why the universe appears smooth and continuous to us. It's the quantum equivalent of a high-resolution screen, where the pixels are so fine they're invisible to our eyes. The implications are dizzying. If the holographic principle is true, then the universe isn't just described by information, it is information, a dynamic tapestry of entangled bits playing out on the grandest stage. Black holes aren't just swallowing matter, they're encoding it onto their event horizons like celestial hard drives, and the reason entanglement defies distance. Because in a holographic universe, separation might be an illusion. Particles aren't really far apart at all. They're just flickering projections of the same underlying code. Experiments are already probing this wild idea. Some physicists are using quantum computers to simulate holographic universes, watching how entanglement entropy mirrors the behavior of gravity in lower dimensions. Others are studying the cosmic microwave background, hunting for anomalies that might betray the universe's true, pixelated nature. The holographic principle isn't just a theory anymore, it's a lens reshaping how we see reality itself. And if it's right, the greatest magic trick of all isn't entanglement or black holes. It's the universe convincing us it's 3D when the truth might be written in 2D. In 2018, scientists pushed quantum entanglement to its limits, stretching those ghostly connections across an astonishing 1,200 kilometers, proving that even Earth's curvature couldn't break the bond. The experiment, led by a team in China, sent entangled photons from the MICIUS satellite to ground stations separated by a distance greater than the length of California. But the real triumph wasn't just the distance, it was how flawlessly the particles stayed in sync, their quantum link unbroken despite hurtling through the turbulence of Earth's atmosphere. The results were unambiguous. Entanglement doesn't weaken with space. It's as if the universe hardwired these particles together, indifferent to the miles between them. Yet this was just the warm-up. Physicists are now drafting even bolder tests, aiming to catapult entanglement into the interstellar arena. One audacious proposal involves using quasars, ancient, hyperactive galaxies billions of light years away, as cosmic dice rolls. Here's the plan. 2 labs on Earth would each point telescopes at the same quasar, capturing photons that have traveled since the dawn of time. Because quasars emit light in unpredictable bursts, these photons could serve as nature's random number generators. The labs would use these random cosmic signals to set the measurement angles for their entangled particles. If the particles still match instantaneously, even when their settings are dictated by events billions of years in the past. It would prove entanglement defies not just space but time itself. Skeptics argue the experiment borders on science fiction. Aligning telescopes with enough precision to catch the same quasar photons while accounting for atmospheric interference and cosmic noise is a nightmare of engineering. But supporters counter that the payoff could rewrite physics. If entanglement holds across such scales, it would cement the idea that the universe operates on a level of interconnectedness we're only beginning to grasp. It might even hint that spacetime as we know it is a secondary layer draped over a deeper quantum reality. The debate isn't just academic, it's philosophical. Testing entanglement at cosmic distances forces us to confront whether the universe is fundamentally local, with influences bound by light speed limits, or whether spookiness is woven into its very fabric. Some theorists suggest that if these experiments succeed, we might need to rethink causality itself. Could particles be linked not just across space but outside of time? The answers won't come easy, but the quest is already reshaping how we see the cosmos, and the most thrilling part, the tools to find out are no longer dreams. They're blueprints waiting for humanity to take the next step into the quantum unknown. What if reality itself is just a cosmic popularity contest? That's the startling premise of quantum Darwinism, a theory that suggests the solid, predictable world we see isn't fundamental at all. Instead, it's the result of countless quantum interactions voting on what gets to be real. Here's how it works. At the tiniest scales, particles exist in a haze of possibilities, their positions and states undefined. But the moment they entangle with their environment, air molecules, light particles, even you observing them, those fuzzy quantum states start to collapse into something concrete. It's as if the universe holds an endless election where every interaction is a ballot cast for one outcome over another. When enough votes pile up, we get what we call classical reality. The chair you're sitting on, the screen in front of you, all seemingly fixed in place. Think of it like a game of quantum telephone. A single particle might whisper its state to a nearby photon, which then tells a dust mote, which nudges an air molecule, on and on until millions of copies of that original quantum state exist in the environment. The version that gets repeated most becomes the winner, the one we perceive as real. This isn't just philosophy. Lab experiments with quantum dots and delicate sensors show how fragile superpositions give way to definite states as more environmental particles become entangled. The more observers there are, even if they're just stray atoms, the faster quantum weirdness fades into everyday normality. The genius of quantum Darwinism is how it bridges the quantum and classical worlds. We've long struggled to explain why quantum effects vanish at larger scales. Why don't cats, cars, or continents exist in superpositions? The answer might be entanglement's exponential reach. A single electron can be in two places at once, but when it's surrounded by trillions of particles all interacting with it, those multiple states can't survive the scrutiny. It's like trying to keep a secret in a crowded room. The truth inevitably leaks out. Here's where it gets even wilder. This process doesn't just explain reality's solidity, it hints that what we perceive is just a shadow of the quantum underworld. The properties we think of as fundamental position, momentum, even time, might just be the most popular votes in an endless cosmic tally. Alternate outcomes don't disappear, they're drowned out by the noise of entanglement, like faint radio stations lost between stronger signals. And the implications ripple far beyond physics labs. If quantum Darwinism holds, our entire experience of the universe might be a collective hallucination shaped by the trillion tiny hands of entanglement. The moon isn't there because it's solid, it's there because enough particles have agreed on its position. This isn't just science, it's a revolution in how we understand existence itself, proving once again that entanglement isn't just a quirk of tiny particles. It's the scaffolding of reality, quietly holding up the world we think we know. Imagine two strangers on opposite sides of the planet suddenly sharing a secret language without ever meeting or exchanging a single word. That's the magic of entanglement swapping, where particles become mysteriously linked despite having zero direct interaction. To pull off this quantum telepathy, scientists deploy a third particle as a cosmic messenger, creating a chain reaction that defies classical logic. Here's how it works. Start with two pairs of entangled particles. Let's call them pair A particles 1 and 2, and pair B particles 3 and 4. Particles 1 and 4 have never met, but particles 2 and 3 are brought together in the lab and subjected to a special quantum operation called a Bell state measurement. When these middlemen particles are measured, their entanglement is destroyed, but the act of measurement forges an instant link between particles 1 and 4, the original outsiders. It's like two pen pals communicating through a mutual friend who vanishes the moment they hand over the letter, leaving the distant duo perfectly synchronized. The brilliance of this trick lies in its relay-like efficiency. Picture a quantum version of the Olympic torch ceremony, where the flame isn't passed from runner to runner but teleported between them. Particle 2 carries entanglement from its original partner, particle 1, to the intermediary, particle 3, which then passes the baton to particle 4, all without particles 1 and 4 ever sharing a physical connection. The measurement of the middle particles acts as a trigger, collapsing their states while simultaneously stitching together the ends of the chain. This isn't just theoretical. Labs have demonstrated entanglement swapping with photons, beaming one half of a pair through fiber optic cables while its future partner waits miles away, oblivious until the quantum handshake completes. What makes this process so revolutionary is its scalability. By daisy-chaining entanglement swaps, researchers could one day build a quantum internet where information hops between cities, or even planets via a network of these invisible relays. Imagine a future Mars colony receiving Earth's data through a cascade of swapped entangled particles, each link in the chain extending the reach of secure communication. The distances wouldn't matter because entanglement doesn't care about space. It's as if the universe provided a cheat code for bypassing the speed of light, at least for correlation. But the real head spinner, entanglement swapping, hints at a deeper truth. Quantum connections might not depend on proximity or history at all. Particles don't need to know each other to fall into sync. They just need to be part of a larger web where measurement alone can rewrite their relationships. This flips our classical intuition on its head. In everyday life, connections require contact, a handshake, a wire, a signal. In the quantum realm, the mere act of looking can forge bonds across the void, as if reality itself is a vast game of dominoes where touching one tile topples another, no matter how far apart they lie. And here's the kicker, this isn't just a lab curiosity. Entanglement swapping is already being tested in space-based quantum networks, where satellites act as hubs for these ephemeral handoffs. The goal, a global infrastructure where encryption keys, medical data, and financial transactions flow through a web of particles linked by nothing but the universe's spookiest phenomenon. The takeaway is clear. In the quantum world, absence doesn't break a connection, it defines it. The particles that seem the most isolated might be the ones whispering closest secrets, tied together by the ghostly threads of entanglement swapping. Even the strongest quantum connections aren't invincible, they're fragile, like whispers in a storm. This vulnerability has a name: quantum decoherence, the process where entangled particles lose their magical synchronization because of tiny, unavoidable nudges from the world around them. Picture a perfectly tuned radio station suddenly dissolving into static as you drive through a tunnel. That's decoherence in action, the pristine quantum signal of entanglement getting drowned out by the noise of reality. At its core, decoherence happens when an entangled particle interacts with its environment, whether it's a stray photon, a passing air molecule, or even the warmth of the room. These interactions act like pebbles tossed into a still pond, rippling through the particle's delicate quantum state and scrambling its connection to its partner. Unlike classical systems where disturbances might just distort information, quantum systems face an existential threat: the superposition, that ethereal state of being both this and that simultaneously collapses into something ordinary, like a spinning coin finally settling on heads or tails. And once that happens, the entanglement is gone, poof. The real challenge isn't just that decoherence exists, it's how easily it happens. In labs, scientists go to heroic lengths to shield quantum systems from the outside world. Superconducting qubits operate at temperatures colder than deep space, suspended in vacuum chambers to avoid even the slightest vibration. Ion traps use lasers to levitate atoms, suspending them in near-perfect isolation. But the moment protection falters, say, a stray microwave photon sneaks in, everything falls apart. It's like trying to balance a house of cards in a breeze. Yet decoherence isn't just a nuisance, it's a clue. The fact that quantum states are so easily disrupted tells us something profound about the boundary between the quantum and classical worlds. In a sense, decoherence is why we don't see cats or cars in superpositions. The larger an object, the more environmental interactions it has, and the faster its quantum weirdness evaporates. A single electron might stay entangled for milliseconds, but a speck of dust, its quantum features would vanish in a flash. But here's the twist: decoherence doesn't mean quantum effects are destroyed, they're just spread out. Imagine a drop of ink in a glass of water. At first, the ink is concentrated, visible. Stir the water, and the ink disperses, becoming impossible to track. But it's still there, just entangled with countless water molecules. Similarly, when a quantum system decoheres, its information doesn't disappear. It leaks into the environment, woven into the fabric of everything around it. Some scientists even argue this is how classical reality emerges, through countless tiny quantum interactions, adding up to something stable and predictable. The battle against decoherence is driving some of the most cutting-edge breakthroughs in quantum tech. Error-correcting codes inspired by how nature might protect quantum information in photosynthesis are being tested in quantum computers. Researchers are designing materials with quiet environments where coherence can last longer, and some are even turning decoherence into a tool, using it to study how quantum systems transition into classical ones. So while decoherence might seem like the villain in the quantum story, it's also a teacher. It shows us where the quantum world ends and ours begins, and how, with enough ingenuity, we might one day bridge the gap. Because if we can tame decoherence, the possibilities are as vast as entanglement itself. What if the next generation of telescopes didn't just see the universe but felt it, using the ghostly whispers of entangled photons to pierce through cosmic fog? NASA quantum imaging projects are turning this sci-fi dream into blueprints, with entanglement-enhanced telescopes poised to shatter the diffraction limits that have constrained astronomers for centuries. Here's the problem classical telescopes face. Light from distant stars spreads out as it travels, blurring fine details like the surface of an exoplanet into a pixelated mess. Even the mighty James Webb Space Telescope hits a wall. It can't resolve features smaller than the wavelength of light it captures, but quantum entanglement offers a backdoor. By engineering telescopes that harness entangled photon pairs, scientists could effectively cheat the rules of optics, squeezing out details once thought impossible. Picture this: a quantum telescope in orbit fires one photon from an entangled pair toward a distant exoplanet, while keeping its twin locked safely on board. When the outgoing photon bounces off the planet's atmosphere and returns, its entangled sibling still in the telescope retains a memory of its partner's journey. By comparing the two, researchers can reconstruct the exoplanet's surface with absurd precision, like dedsing the texture of a golf ball from a single grain of sand. This technique, called quantum interferometry, bypasses the blurring effects of diffraction entirely, leveraging entanglement to extract information that classical light alone could never reveal. NASA Quantum-Enhanced Optical Communication Team isn't just theorizing, they're prototyping. One concept involves pairing traditional mirrors with quantum light sources, creating hybrid observatories where entangled photons act as cosmic spies, sneaking past the usual resolution barriers. Early simulations suggest such systems could distinguish cloud patterns on Proxima Centauri b, or even volcanic plumes on Earth-sized worlds dozens of light-years away. The key lies in entanglement's non-local magic. Measurements of one photon instantly narrow down the possibilities for its twin, sharpening the final image like a focus dial cranked to infinity. But the real game-changer, noise immunity. Classical telescopes drown in stray photons from cosmic background radiation and nearby stars. Entangled photons, though, carry a unique signature, like a secret handshake allowing detectors to filter out everything but the quantum-coupled pairs. It's the equivalent of listening to a whisper in a hurricane by tuning into only the exact pitch of the speaker's voice. NASA roadmap hints at lunar-based quantum telescopes within decades, free from Earth's atmospheric interference, where entangled photons could map alien continents or trace methane oceans on icy moons. The implications stretch beyond astronomy. Quantum imaging could revolutionize medicine, letting MRI machines peer into tissues at cellular resolution, or transform surveillance by spotting stealth aircraft from orbit. Yet the most profound revelation might be philosophical. If entanglement can let us see farther, it's proof that the universe's hidden wiring isn't just real, it's usable. Telescopes of the future won't just observe the cosmos, they'll eavesdrop on its deepest conversations, one entangled photon at a time. Quantum entanglement doesn't just challenge physics, it rattles the very foundations of how we perceive reality. For centuries, Western science has championed reductionism, the idea that to understand the whole, you dissect its parts. But entanglement whispers a radically different story, that the universe might be fundamentally interconnected, a seamless tapestry where separation is an illusion. David Bohm, the visionary physicist, called this the implicate order, a hidden dimension where everything is enfolded into an undivided whole. In his view, particles only appear separate because we're observing the unfolded surface layer of reality. Beneath it, like currents in a river, lies a deeper flow where entanglement reigns. The world is a hologram, Bohm argued, where each part contains the whole. This idea eerily echoes ancient Eastern philosophies. Hinduism's concept of Brahman, an all-encompassing cosmic oneness, mirrors entanglement's insistence that particles share a unified existence. The Buddhist notion of dependent origination, where nothing exists independently, could be a poetic translation of quantum non-locality. Even Lao Tzu's Taoist teachings, with their emphasis on harmony and interconnectedness, feel like prophecies of a quantum universe. The Tao is the one, he wrote, from which all opposites arise. Replace Tao with quantum field, and the parallels become uncanny, but here's where it gets provocative. If entanglement proves that particles can't be described individually, only relationally, does that mean consciousness itself plays a role in shaping reality? Some interpretations of quantum mechanics, like the participatory anthropic principle, suggest that observation isn't just passive, it's creative. The act of measuring a particle's state might not reveal pre-existing properties but generate them, like a sculptor chiseling form from marble. This doesn't imply solipsism, that we're dreaming the world into being, but rather that reality is a collaborative dance between observer and observed. Critics argue this veers into metaphysics, but the math refuses to dismiss it. Bell's theorem buried the idea of local hidden variables, leaving us with a universe where connection precedes separation. Even pragmatic physicists like Carlo Rovelli, architect of loop quantum gravity, admit that relationality, the idea that properties only exist in relation to other things, might be fundamental. An electron's spin isn't a thing, Rovelli says. It's an answer to a question asked by another system. The implications ripple far beyond labs and equations. If entanglement is universal, then the boundaries we take for granted between self and world, mind and matter might be porous. Ecological systems, social networks, even human relationships could all be threads in the same quantum weave. Indigenous cultures have long spoken of this kinship. Modern physics is now catching up. The Navajo phrase haja, often translated as walking in beauty, describes a state of harmony where all life is reciprocally linked. It's entanglement not as equations but as lived wisdom, yet the universe resists easy metaphors. Bohm's implicate order isn't mysticism, it's a mathematical framework. The danger lies in conflating poetic resonance with proof, but perhaps that's the gift of entanglement. It forces us to hold multiple truths at once. The universe is measurable and mysterious, particle and wave, separate and united. In the end, the greatest revelation might not be a theory or a philosophy, but humility. The recognition that reality, in its infinite depth, will always outrun our attempts to pin it down. And that, perhaps, is the most entangled truth of all. From Einstein's dismissive, spooky action to the quantum revolution reshaping our world today, entanglement has defied every expectation. What began as a theoretical debate between giants like Bohr and Schrödinger has exploded into labs, satellites, and even our understanding of reality itself. We've watched particles whisper across continents, glimpsed black holes linked by wormholes of entanglement, and harnessed this phenomenon to build unhackable networks and computers that defy classical limits. The journey from skepticism to cornerstone of modern physics isn't just a scientific triumph, it's a testament to humanity's relentless curiosity. But here's the thrilling part, we're only scratching the surface. Imagine entanglement-powered sensors detecting earthquakes before they strike, or quantum telescopes mapping alien oceans light years away. Picture a global internet where data leaps between continents instantaneously, not through cables but through the universe's hidden quantum fabric. The same phenomenon that baffled Einstein could one day connect colonies on Mars or reveal the secrets of dark matter. This isn't just science, it's the future unfolding. And it's yours to explore, so tell us, where do you think entanglement will take us next? Will we uncover deeper layers of reality or stumble upon even spookier phenomena? Drop your wildest quantum theories in the comments, because the next chapter of this story isn't just being written by physicists in labs. It's being shaped by dreamers, thinkers, and explorers like you. The quantum revolution isn't coming, it's here, and the most exciting discoveries, they're still waiting to be entangled.